Final section for Unit 5, Section 5.5. We're calling this multiple identity and product to sum formulas. So we're adding some more formulas to our arsenal. So our objectives, our goals are to use multiple angle formulas to solve trig equations. We're going to also use multiple angle formulas to evaluate trig expressions. And finally, we're going to use product to sum and sum to product formulas to rewrite and or solve trig expressions. So lots of solving, lots of evaluating, all that good stuff. So let's start off with these things called double angle formulas. So at this point of the game, let's see if we can apply these next couple formulas to work with different problems. Like sometimes we just have to break things down a little bit. So double angle formulas, we got a sine of 2 times some angle u. We can split it up into 2 times the sine of u times cosine. Now on the kind of going to the right over here to cosine of 2u. Cosine of 2u we could express as cosine squared minus sine squared. Or if you were to kind of apply the Pythagorean identity to it, it would end up being 2 times the cosine squared minus 1, or 1 minus 2 times the sine squared of u. So it's like applying the Pythagorean identity to that original one where you replace cosine, the other one where you're replacing sine. I did that in the wrong order, but you know what I mean. The tangent of 2 times u is equal to 2 times the tangent of angle u over 1 minus the tangent squared of angle u. Essentially, anytime you see an angle or double angle, you're going to want to use these and you're going to want to identify what u is. So starting off with example 1, we're asked to solve 2 times the cosine of x plus the sine of 2x equals 0. Now we're going to replace that sine of 2x. That's going to be one of our double angle identities. And we're going to kind of follow this pattern here. So it's going to be equal to, pardon me, 2 times the sine of u times the cosine of u. So in this case, it's kind of like our u is just x. So let's leave that original one, 2 cosine of x alone. Plus, and now we're going to replace sine of 2x with that 2 sine of u cosine of u. So we got 2 sine of our u in this case is x, and it's going to be times the cosine of u, or in this case the cosine of x. And that's all equal to 0. Now from here, you'll notice in both of these we have a 2 and a cosine. So we can factor out a 2 and a cosine from both of those, which will give us 2 times the cosine of x. And then when we factor it out of both those groups, we're left with 1 plus the sine of x. All that's equal to 0. So now we have two things multiplied by each other equal to 0. That means either this first group, 2 cosine of x, equals 0, or the other group, 1 plus the sine of x, equals 0. I'm going to solve the one with cosine first. If we divide both sides by 2, we got cosine of x equals 0. And then we go to our unit circle, and we figure out where the cosine is equal to 0. Well, on our unit circle, sorry, I've got a lot of notes here from previous things. Let me delete that. So the cosine is where x is equal to, the cosine on our unit circle is the x value. So from here, we can say our x is either at pi over 2 when x equals 0, or at 3 pi over 2, because that's where cosine is equal to 0. So we got two answers right there. Now, for the other one, we're asked to figure out where sine is equal to, or 1 plus sine is equal to 0. So if we subtract 1 from both sides, we got sine of x equals negative 1. Now, from there, we can just go to the unit circle. Again, looking for where the sine of x equals negative 1. That's down here at 3 pi over 2, because we have the sine, the y value, is negative 1. So, the other answer, sorry, I keep going to the wrong notes, is x equals 3 over 2. Sorry, 3 pi over 2. Now, folks, we already had that. So we don't need to list it twice. So we can say our final answers are x equals pi over 2 and 3 pi over 2. Applying this in a little different context, we're going to take a look at example 2 here. It says, use the following to find the sine of 2 times theta, the cosine of 2 times theta, and the tangent of 2 times theta. So the first thing we have is cosine of theta equals 5 pi over 3, and we're told that our domain restriction, we're only looking at angles between 3 pi over 2 and 2 pi. In other words, angles in quadrant 4. So let's start off with the sine version. So we got the sine of 2 theta. Following along with that double angle identity on the previous page, it's going to be 2 times the sine of theta times the cosine of theta. Well, the nice thing is we already know the cosine of theta. That's 5 over 13. But what we don't know is the sine of theta. Now, we can figure it out actually reasonably easily by drawing a right triangle. trig functions always kind of relate back to right triangles. So let's say in this right triangle that I drew up at the top here, let's say this is angle theta. Now, if we know the cosine of angle theta is equal to 5 over 13, that's your adjacent side over your hypotenuse. And so let's label that. So we got adjacent, and we got our hypotenuse, and then the tall side in this case is our opposite. And our adjacent side we got was 5, our hypotenuse is 13. We need to figure out what the opposite side is. Now, good old Pythagoras, not only does he have those identities that we've been using, he came up with that Pythagorean theorem of one leg squared plus the other leg squared equals the hypotenuse squared. So let's plug in what we know. I'm just going to call the adjacent side A. I'm going to call that, so we got 5 squared plus our opposite side we don't know is B squared equals 13 squared. Now, cleaning this up a little bit, we got 25 plus B squared equals 169. If we subtract 25 from both sides, we got B squared equals 144. And then we take the square root of both sides, and we end up with B equals, the square root of 144 is 12. Now, one thing we actually need to pay attention to is this domain restriction of 3 pi over 2 and 2 pi. So we're working in quadrant 4. So in quadrant 4, we're talking about the B value, which is our height. It's actually going to be a negative height. So in this case, we're going to say our B value is negative 12 because the Y value is in quadrant 4. So the sine value, the Y value is in quadrant 4, so we got to be dealing with a negative value there. Let me rewrite that a second. So it's negative 12. So then, for this example here, the sine of 2 theta, we still don't know what theta is, and we're not going to figure it out, honestly. But it's equal to 2 times our sine. Now we have the opposite side. I didn't label that on the triangle, but let me do that a second. We ended up with negative 12. So it's going to be negative 12 over 13. So it's 2 times negative 12 over 13 times 5 over 13. If we're putting these, or if we're multiplying all these are all just fractions. Our denominator ends up being 169, 1 times 13 times 13. And our numerator is 2 times 12, which is negative 24, times 5 gives us negative 120. So the sine of 2 times theta is negative 120 over 169. We're also asked to find the cosine of 2 theta. We still, again, don't know what theta is, and really, it doesn't really matter what theta is because we can still do everything without it. So the cosine of 2 times theta, there are several different options. I'm just going to go with the first one. We were told it's cosine squared of theta minus sine squared of theta. It actually doesn't make a difference which one you use. I can show you, or I'll show you the other ones right quick after this. But cosine squared, we already know what cosine is. So cosine is 5 over 13, and we're going to square that. Minus sine squared, well, sine is negative 12 over 13, and we're going to square that. So cleaning this up a little bit, 5 over 13 squared, so the 5 squared is 25, 13 squared is 169, minus negative 12 squared is 144, and then again 13 squared is 169. When we subtract these, 25 minus 144, putting these into one fraction, is negative 119 over the common denominator of 169. So our cosine of 2 theta equals negative 119 over 169. Now again, if you use one of the other versions, it doesn't make a difference. So if you were to do like 2 cosine squared minus 1, let me do that one right quick. So I'll say cosine of 2 theta equals 2 cosine squared of theta minus 1. Well, we know cosine squared is, 5 over 13, and we're squaring that, and we're subtracting 1. So this would be 2 times 25 over 169, not 196, 169, minus 1, which would give us 50 over 169. And then we got to subtract 1, but we're going to write 1 as 169 over 169. And when we subtract those, we end up with negative 119 over 169. So it really doesn't matter which version of the formula we use. We get the same answer either way. You can use the third one. I'm running out of space, so I'm not going to. The tangent, that's the last one we're asked to find. The tangent of 2 theta, let me draw another line here. The tangent of 2 times theta is equal to, we're told it's the sine of 2 theta over the cosine of 2 theta. We had a couple options for that. Or, sorry, I'm misremembering. So again, it's, I'm jumping ahead. So we do have this formula, but we still need to figure out what theta is. So we need to figure out what the u value is, which we don't know. And you already need to know what tangent is. So we can just do the tangent of 2 theta equals the sine of 2 theta over the cosine of 2 theta. It's much, much easier. So tangent is always equal to sine over cosine. Sine of 2 theta, we found out was negative 120 over 169. And then we're going to divide that by the cosine of 2 theta, which we ended up finding was negative 119 over 169. Dividing by fractions, not ideal. So what we're going to do instead is we're going to take that numerator, negative 120 over 169, and multiply it by the reciprocal of the denominator. So we got 169 over negative 119. It's nice that the 169s cancel out, and we're left with just negative 120 over negative 119. If you want to clean that up just a little bit more, that's a positive 120 over 119. So if you already know the sine and cosine, just use those to find the tangent.